The magnetic dipole moment of revolving electron in an hydrogen atom. This is 5 mark question. So we need to calculate dipole moment of revolving electron. So dipole moment. So what is dipole moment? We just studied M is equal to product of current and area vector. This is called as magnetic dipole moment, right? So an electron revolving around the nucleus possesses a dipole moment and a system acts like a tiny magnet. So here you are observing there is an electron. It is revolving around the nucleus. The nucleus charge they have given it, plus that is a charge of a nucleus, and r is the radius of an atom. So electron is revolving around the nucleus. So electron is nothing but a charge, negative charge. The charge is moving. Whenever charge is moving, that produces a current, and that is the current here. That current it is. And what about A? A is the area of the loop, this particular loop where the current is flowing. This is a current, right? Electron is revolving here, that means the current is flowing in it. The current is flowing. Therefore, the current we already have in a circular loop. Area. What is area of this circular loop? The area of circular loop is pi. Radius is r, pi r square. That's also is there. So magnetic moment is easy to calculate. So magnetic moment is equal to current into area. But what is the direction of magnetic moment? The magnetic moment is a vector quantity. Its direction can be found by using a right hand thumb rule, where what you need to do, you have to curl your finger in the direction of current. We have to curl our finger in the direction of current. Here, what is the direction of current? So, if the electron, all the electrons are flowing, if the electron is flowing in this direction, that means the current is opposite, like this. The current is in clockwise direction. So, you have to curl your finger in the direction of current, and where the thumb points into the plane of the paper, right? Into the plane of the paper where I am writing. So that is the direction of magnetic dipole moment. What to do? We have to apply right hand thumb rule. Right hand thumb rule. We already discussed about it in earlier class. Just have a look at those videos and come. So what to do? Curl your finger in the direction of current, and where the thumb point inward inside the plane of the paper. So this is the direction of the dipole moment, magnetic dipole moment. Now I need to calculate first I, and area already found it. The value of area enclosed by the current is pi r square. So I need to calculate the current now. Therefore, we know the current formula. Why current? Where do you get the current? Since the charge is moving, electron is moving, that produces a current. So the current I is equal to Q divided by T, very basic formula of the current. By the definition of current it is. But here Q is the charge of an electron, E, divided by T I am going to write, where T is the time period of an electron. So time taken by the electron to complete one revolution is called as time period. So I is equal to E by T. This is a current. Now I need to calculate what is the time period now. So time period. First I want to solve for T now. So we have T is equal to, can I write the time taken to move is distance divided by velocity, because we know that velocity or speed is equal to distance traveled divided by time taken. So then what is time taken is equal to distance divided by speed. So I'm using that here. So time period t is equal to distance covered by the electron. How much distance the electron covers once it complete one revolution. 2 pi r distance it covers, right? Circumference of the circular path 2 pi r divided by speed is v. So we got very easily the time period. Then this time period can be taken and substituted for t in this particular equation. I will call this as equation 2 and this as equation 1. Okay, now therefore I is equal to E divided by t value is 2 pi r divided by v. So that value I am taking it to the numerator, EV we are going to get. So I value we found and a value also we already got it here, pi r square. Now the equation 1 becomes, maybe substitute equation 3 in equation 1. So the equation becomes, so m is equal to, what is the value of I we got? E into v divided by 2 pi r, and what is the value of a? Pi r square. Okay, here the value of 1r and 1r will be cancelled and pi also got cancelled. Therefore the magnetic moment m is equal to evr divided by 2. Okay, this is the expression for magnetic moment. I want to simplify it further. Now what can I do? I will just multiply and divide it by mass of an electron. Multiply and divide it by mass of an electron. I will write EME because already one m is here. So ME is the mass of an electron. So it becomes m is equal to E as it is. I will write ME multiplied and I am going to divide it to ME. So what is this term? MVR. MVR. What is this term is? This term is nothing but angular momentum. We studied in the first year. So MVR is angular momentum. Therefore, M is equal to magnetic dipole moment. M is equal to E divided by 2ME times L. And this is an expression for, final expression for the magnetic dipole moment of revolving electron. In vector form, since magnetic moment is a vector, in vector form we can write in vector form M is equal to minus E divided by 2ME times the angular momentum vector. Minus E is the charge of an electron. Here negative sign indicates that angular momentum of electron is opposite in the direction of the magnetic moment. That is the negative sign here. Okay, now I am going to apply the Bohr's postulates here. One of the Bohr's postulate I will take. So we have, according to Bohr's postulate, according to Bohr, the angular momentum of revolving electron is equal to nh divided by 2 pi, where n is equal to 1, 2, 3, so on. First orbit, second orbit, third orbit of an electron. Now the magnetic moment becomes M is equal to E divided by 2 m NH divided by 2 pi. If n is equal to 1, if you take n is equal to 1, what you are going to get? If n is equal to 1 for first orbit, the magnetic moment M is equal to EH divided by 2 into 2, which is 4 pi ME. And this value, if you substitute the value of standard values of these constants, what you are going to get? We will see that the value comes out to be 9.27 into 10 to the power minus 27 ampere meter square. How you will get this? Because we know the value of standard constants here. So E is charge of an electron is 1.6 into 10 to the power minus 19, and H is Planck's constant. This is 6.625 into 10 to the power minus 34 joule second. This is Coulomb, and pi value is just a constant 3.142, and mass of an electron is equal to 9.1 into 10 to the power minus 34 kg. If you substitute all these values into the above equation, you will get this number, and this number is called as, this value is called as Bohr magneton. Bohr magneton. And from this relation, I will bring this relation now. From this relation, this ratio, you just transfer L on the other side. So M divided by L is equal to E divided by 2ME. And this ratio, magnetic moment to the angular momentum, is called as one ratio called as gyromagnetic ratio. It is called as gyromagnetic ratio, and its value found that 8.8 into 10 to the power 10 coulomb per kg for an electron. So this ratio is called as gyromagnetic ratio. It is denoted by gamma. Okay. So here only it is there. This is the value of Bohr magneton. Okay, this is one more concept.